This surprising Earth theory could protect Mars from Earth's microbes. As humanity prepares for longer journeys into the cosmos, a growing concern continues to echo through scientific circles. How do we ensure that Earth's microscopic life doesn't hitch a ride and contaminate other planets? Traditionally, our planetary protection strategies have been built on mathematical models, statistical frameworks that try to quantify risk in terms of probability. Agencies like NASA, for instance, have set strict contamination thresholds. For a mission to Mars, the chance that a single mission would allow Earth's microbes to contaminate the red planet must be less than 0.1%. It sounds precise. It sounds safe. But is it enough? A recent study proposes a fundamental shift in how we think about protecting alien worlds from Earth-based contamination. Rather than relying on abstract probability models, researchers Daniel J. Breener and Charles S. Cockle suggest we turn to something more familiar, and surprisingly relevant, the science of island biogeography. Why islands? Because planets, much like remote islands on Earth, are physically isolated environments. And on islands, colonization doesn't depend purely on the number of seeds or organisms arriving, it depends on whether those organisms can find conditions suitable to survive, grow, and reproduce. The analogy is striking. Just as an island in the ocean may or may not support a new plant species, a planet like Mars may or may not allow a terrestrial microbe to persist. The question is no longer, what are the odds that a microbe makes it to Mars? It's, can that microbe actually live there once it arrives? The researchers argue that focusing solely on reducing microbial load and estimating survival odds misses a deeper biological reality. The true bottleneck in contamination isn't the trip, it's the aftermath. If a microbe lands in a place where the temperature is too low, the pressure too weak, or nutrients too scarce, it won't matter how many microbes arrive. They'll simply die out. No contamination. No colonization. This leads to a key insight: microbial colonization is not a probability curve, it's a binary outcome. Either the microbe survives and reproduces, or it doesn't. And whether it does depends entirely on whether the environmental conditions allow the population to persist long enough to establish itself. This concept is known as the mean time to extinction. If the death rate consistently exceeds the birth rate, the microbial presence fades over time. But if reproduction is possible, even a single surviving microbe might spark a population that takes hold. This approach encourages a more detailed, condition-based analysis of contamination risk. It suggests we shift away from abstract models and instead ask a more basic, biological question: is the target environment one in which Earth microbes could live? And if the answer is no, perhaps we don't need to invest so heavily in sterilization. But if the answer is yes, then strict planetary protection protocols become absolutely essential. The implications are particularly relevant for Mars. Mars presents a combination of hostile conditions: severe cold, thin atmosphere, intense radiation, and perchlorate-laden soil, that would challenge almost any form of terrestrial life. Still, there may be a few extremophiles, organisms from Earth that can survive in extreme conditions, that could beat those odds. According to the researchers, it would be valuable to create a comprehensive catalog of known Earth microbes, matched with the kinds of environments they can endure. With that information, mission planners can make informed decisions about which organisms actually pose a contamination risk and which do not. This rethinking doesn't discard traditional planetary protection. Instead, it refines it. It asks for a more targeted approach, one based on known biological thresholds, not just statistical predictions. By identifying whether specific microbes could survive under Martian, Europan, or other extraterrestrial conditions, we could focus our resources more effectively, prioritize key sterilization measures, and perhaps even relax protocols when there's no real threat of microbial survival. Ultimately, what this new perspective provides is a way to align planetary protection with the foundational principles of ecology and evolutionary biology. It's a recognition that contamination isn't just a numbers game, it's an environmental one. An understanding that distinction could help us safeguard other worlds more wisely. As we step forward into this new era of interplanetary exploration, the lessons of Earth's islands may serve as our best guide. By learning from how species succeed or fail to colonize isolated environments here at home, we can better predict what might happen millions of kilometers away. Still, even as the models grow more nuanced and the science more refined, one age-old idea lingers in the background, one that scientists and storytellers alike have repeated for generations: life finds a way. And if that's true, then our responsibility isn't just to explore carefully, but to think deeply about the consequences of every landing, every drill, and every sample. Not just because of what we might bring back, but because of what we might leave behind. Webb may detect birth of supermassive black holes. Here's how. One of the most enduring mysteries in modern astronomy is how supermassive black holes, some with masses exceeding billions of times that of our Sun, came into existence so soon after the Big Bang. Observations have revealed their presence in galaxies that formed less than 750 million years after the universe began. These celestial giants appear to have grown at astonishing rates, raising fundamental questions about how such massive objects could emerge in such a short cosmic timeframe. Under the traditional model, black holes form from the remnants of massive stars that collapse at the end of their lives. These stellar mass black holes typically weigh only a few solar masses. To reach the billion solar mass scale observed in the early universe, these remnants would need to accrete matter at extraordinary rates, continuously, for hundreds of millions of years, an implausible scenario given what we know about the limitations of matter inflow and energy feedback in galactic environments. However, a new theoretical approach may hold the key. A team of scientists has explored a radically different path, known as the direct collapse scenario, whereby massive clouds of primordial gas, under specific conditions, can collapse directly into black holes without forming stars first. This model offers a more feasible mechanism to produce black hole seeds in the range of 100,000 to 10 million solar masses. From such a starting point, it's far more plausible for these seeds to evolve into the supermassive black holes we observe in the early cosmos. Researchers Yang Luo and Isaac Schlossman have presented new simulations that suggest these direct collapse black holes, still in their formative stages, may actually be observable, if we know what to look for. Their work focuses on identifying a unique signal, Lyman-alpha emission, a particular kind of ultraviolet light produced when hydrogen atoms absorb and re-emit energy. This emission is one of the key cooling mechanisms in primordial gas clouds. During a direct collapse event, the Lyman-alpha signal not only represents the gas shedding heat, but may also provide a distinctive observational signature that could reveal the presence of a forming black hole. But there's a catch. In early models of direct collapse, the gas clouds were assumed to collapse spherically. In such scenarios, Lyman-alpha photons would be trapped, scattered, and eventually destroyed due to resonant absorption processes, making detection impossible. Luo and Schlossman propose a more realistic model, one that incorporates angular momentum and rotational dynamics. In this scenario, the collapsing gas forms an accretion disk around a dense central region. As the disk feeds the growing object, it also generates powerful biconical outflows, narrow regions along the poles where gas is blown outward, creating escape channels for Lyman-alpha photons. Their computer simulations show that more than 95% of Lyman-alpha radiation could escape through these outflow regions, making it detectable from Earth-based or space-based telescopes. At redshift 10, when the universe was just about 500 million years old, this kind of emission could serve as a beacon pointing to the birth of a supermassive black hole. What makes this signal particularly compelling is its spectral shape. The researchers found that the Lyman-alpha lines from direct collapse objects would appear highly asymmetric, with a pronounced redshifted tail. This is in stark contrast to the symmetric profiles typically observed in star-forming galaxies or even quasars. These features would serve as a fingerprint, allowing astronomers to distinguish direct collapse objects from other luminous sources in the universe. The James Webb Space Telescope, with its NIRSpec instrument, is especially well-equipped to hunt for such signals. Using its multi-object spectroscopy mode, Webb could potentially detect these unique Lyman-alpha emissions with roughly 10,000 seconds of integration time. This opens an exciting new observational window into the universe's earliest and most extreme phenomena. Equally important is the timing of these emissions. The Lyman-alpha signal is likely emitted during a very narrow phase, before the object becomes a fully formed black hole with an accretion disk and metallic content. In this sense, the opportunity to observe these direct collapse objects is fleeting. It would require strategic, deep field surveys that are both wide and targeted to capture these short-lived events. If successfully detected, such emissions would not only validate the direct collapse hypothesis but also redefine our understanding of black hole formation. They would provide concrete evidence of a mechanism capable of creating the massive seeds that ultimately evolved into the gravitational giants shaping the structure of galaxies. The discovery of even a single direct collapse object would mark a pivotal moment in astrophysics, bridging the gap between theoretical models and observable cosmic phenomena. In a universe filled with enigmatic events and extraordinary objects, the ability to witness the birth of a supermassive black hole would stand as a milestone in our quest to understand cosmic origins. The James Webb Space Telescope might not just be a tool for observing ancient galaxies, it could be the key to witnessing the most dramatic moments in the universe's early history, as colossal black holes began to awaken from clouds of pristine hydrogen.